Hey there, welcome back to the channel. So this is Ramandeep Singh, and we will continue in the CSES problem solving sessions. And in this video lecture, we're going to be solving the next problem in the series, and the problem name is round trip, right? That problem we're going to be solving in this video, and this problem is also easy. So again, we are still on DFS and BFS. We don't require any new algorithm to solve these problems, to solve even this problem as well. We just need a plain DFS. If you know how to count connected components, how to perform DFS over a graph, then like how the DFS actually work. If you can easily visualize a DFS, how it actually work, how the call stack is being filled, how the function is recursively called, and then you can easily solve this problem with a little bit of critical thinking. You know, of course, not every problem is same. There is some change uh, in a problem. Like, you will not get all the problems as standard problems. So, but usually the thing is, we have limited patterns. We have limited patterns in all the problems. You go to code forces, you go to code chef, you go to maybe top coder, at coder, anywhere you go, you pick any problem. That problem is a variation of some previously existing problem. The variation may match 50%, it may match 60%, it may match 70%, but usually the patterns are limited. The patterns are limited, and uh, we don't have to solve every problem, but we just have to understand the underlying patterns, right? Solving, I think, 300 to 400 problems with the, I would say, open mind, or with the better word is, uh, what would be the better word? Uh, Enlightened mind. With an enlightened mind, if you can solve 300 to 400 problems, then you can solve every problem, right? You can solve every problem. So in order to get better at problem solving, you first has to get that enlightenment here, ठीक है. So without wasting any more time, let's move to the problem solving part. So hey there, welcome back. So let's start solving this problem, that is round trip, and here we're gonna solve this problem. Yeah, round trip. So this problem is also an easy problem, as we have said. You must know what is depth first search in order to solve this problem, and if you know depth first search, you can go ahead and try solving it. Now, Byteland has n cities and m roads between them. Again, we are visiting Byteland. I don't know why this problem setter don't have any other city or the state to visit. This person always visits Byteland again and again. Good. Byteland has n cities and m roads between them. Your task is to design a round trip that begins in a city, goes through two or more other cities, and finally returns to the starting city. So your task in this problem is to design a round trip that begins in a city A. Let's say the city where you begin is A, goes through a couple of cities, है two cities or more cities, and finally returns to the starting city. Every intermediate city on the route has to be distinct. So if you visit one city while you are visiting cities, you can't visit the same city again, right? So that's what you have to do, and you need to come back to the starting city. Basically, it's just like detecting a cycle in a graph, but the graph is undirected, right? So let's understand this with an example. Let's take this example. So we have 5 nodes and 6 edges. So the first edge is between 1 and 3. The second edge is between 1 and 2. Then the third edge is between 5 and 3. So we have an edge between 3 and 5. And then we have an edge between 1 and 5. Okay, so there is an edge between 1 and 5. So let's put 5 here. So बनाते हैं इसको 5 and then there's an edge here, ठीक है, like that. इसको हटाते हैं 1 3 1 5 3 5, then we have 1 5 is there, 1 2 is there, 2 4. So there is an edge between 2 and 4, and then there is an edge between 4 and 5, है ना, ठीक है. 1 and 2, let's say 2 is here, or rather let's make it like this. So 2 is here, and then we have an edge between 4 and 5. So from 2 and 4 there is an edge, so here is an edge here, there is an edge here, 2 and 4, and then there is an edge between 4 and 5, right? Cool. This is the graph that we have. I hope I have drawn the right graph. 1 3 1 2 5 3 1 5, yes, 2 4, yes, and then 2 4 5, yes. So this is the graph that I have at this point, and let's start the DFS. Let's start the DFS, no? Let's start the DFS from here. Now I want to create a round trip. So what is a round trip? Round trip means start at a node. So you have a starting node. Okay, you have a starting node, start node. You start from a node, you go to some nodes, let's say A, then you go to some node B, then you go to some nodes L, and then you come back to the start node, like that. This is a round trip. So let's start from 1. From 1 I move to 5. From 5 I move to 3. From 3 I move to 1. This is a round trip. From 1 I move to 5. From 5 I move to 4. From 4 I move to 2. From 2 I move back to 1. This is also a round trip. So do we have any other constraint apart from this? Your task is to design a round trip that begins in a city, goes through 2 or more other cities, and finally returns to the starting city. Every intermediate city on the route has to be distinct. Obviously, in order for the round trip to be a valid trip, there has to be at least 2 intermediate cities. Like here 1, I can't build a round trip with 1 and 5 only. I need at least 3 nodes in total to build a cycle, है ना? Like moving from 1 to 5, then from 5 to 1 doesn't make sense. It's not a round trip. It's just like going back and forth, back and forth. But we don't want to go back and forth. We start from a node, we move to another node, then we move to another node, and then we come back to the starting node. Okay? And so there we have, we start from 1, we move to 5, we move back to 3, and then we have 1. 1 5 3 1. So what type of 3 5 1 3? Here we have been given 3 5 1 3. 3 5 1 3 is also the same. So this is also, what are valid trips? 1 5 3 1. 3 5 1 3. Then 1 5 4 2 1. This is also, these are valid round trips. These are valid round trips. Okay? You can print any valid solution. Now k doesn't need to be minimum. Okay? K doesn't need to be minimum. Any of these solutions is valid. Now in order to do that, all you need is to just start performing DFS. So perform DFS from node number 1. So let's mark it as visited. So you also take 2 variables. Let's take a start variable, initialize it with -1. Let's take an end variable, initialize this with -1 as well. Now you start at 1. Now from 1, what are the neighbors? 5 4 5 2 and 3. You move to 5. you visit it as well. 5 is also visited. Now what are the neighbors of 5? 4 and 3. Now you move to 3, you visit 3 as well. Now from 3 you move back to 1 because 3 has neighbors as 5 and 1. Now 1 is already visited. You found a neighbor which is already visited, right? And it is also not equal to the previous node from where you have come. Like 3 has, at practically if we see, 3 has two neighbors, 5 and 1, but I'll have to keep track. I do not visit 5 again. So apart from 5, what are the neighbors of 3? 1. And 1 we find is already visited. That means if 1 is visited, I must have visited it before in this particular process which I am going through, right? That means this can be the starting point and the current 3 can be the ending point. So here when I found this type of configuration, I'm gonna reinitialize the start with the neighbor node which was visited, which I found as already visited, and the end node as 3. And once I have start and end, I can always find the cycle. How? I can keep track of the parent or the neighbor or the previous node. So when I started the DFS at 1, the previous node for 1 is -1 because I started from here. Then I moved to 5. For 5 the previous node for 5 becomes 1. So from this is 1, then after 1 we have 2, 3, 4, and then we have 5. These places still contains -1 because they haven't been visited yet. Now from 5 I move to 3. Now for 3 the previous node becomes 5. So 1, then 2, then 3. For 3 the previous node becomes 5. Right? For 3 the previous node becomes 5. So this array we have. Now we come back to 1 and we complete our cycle and we have something in the start variable, we something in the end variable. Now all we need is to start from the end. So this is 1, then we have 2, then we have 3, right? This is 3. Now I print 3, then I print the previous node to 3, which is this, that is 5. Then I move to 5 and I print the previous node of 5, which is 1. Then I move to 1 and I find it -1. I find -1 because there is no previous node to 1. That means the cycle ends here. So finally I print the start node again. The start node was 3, or the end node. I print the end node again. Now I start at 3, then I move to 5, then I move to 1, then I come back to 3. So 3, 5, 1, 3. You can also do reverse. Like you can also do it like start from here, but you don't have the previous of 1. So you can also use a next array. But just don't go into it, but just think of it with the information we already have in the mind, that is using the previous array. We just, while moving from one point to another point, or one vertex to another vertex, I simply store the previous vertex in a variable, in an array, which is this array, and then I simply print the cycle here. So it's a plain depth first search, nothing else. Now we found a cycle right here, but there may be case where we do not find cycle. Like let's say if this edge is missing, we will not find a cycle in this particular visit. 1, 5 and then 1, 3. We don't find the cycle. Now in that case, I will move to 1, 5, and then from 5 I'll move to 4. Then from 4 I'll move to 2. Then from 2 I'll move back to 1. I'll find a cycle here. So in order to do that, now this is also like a case of connected components. We may have disconnected components like this. Let's say we have two components. Now we don't find the cycle in the first component, 1, 3, 1, 5. There is no cycle. Now I start visiting the second component, which is this 2 and 4. So for that I'll have to iterate over every node. So iterate over every node and start the DFS. So start with 1, start DFS. The DFS is going to visit 1, 5 and 3. Then move to 2, start the DFS. This will visit 2. So we'll start the DFS from 2. This will visit 2 and 4. Then we'll try to start the DFS from 3, but 3 is already visited, so DFS what we called. Then from 4 is already visited, 5 is already visited. So in order to handle the connected component thing, we'll have to iterate over every node and try to start the DFS from every node in order to find a valid cycle like this. So this problem is very very simple, and let's jump to the code implementation part. So here we read n and m, the number of nodes and the number of edges. This is my graph. Okay, now I read the graph, and then I'll also need some arrays like vector int visited array, not like vector bool visited array of, then I'll also need a previous array of n plus 1, it contains -1. Then I'll also need uh, a start and start -1 and node -1. Now once I have this thing, I'm going to iterate over every node, and I'm going to start the DFS for that node. The previous is -1, and I'll pass this previous array, I'll pass the visited array, I'll pass the graph. Now this is a boolean function. If there is a cycle starting at this node or ending at this node I, this is going to return true. If there is no cycle, this is going to return false, right? Clear? I hope this thing is clear to all of you people. Now I'm going to call this function only for the nodes which are not visited. So call this function if this returns true, I'm gonna break right here. Now I'll also have to pass the start and end. Let's pass this here, start and end. Now if start is -1 and is -1, then that means you haven't found the cycle, so you print impossible and you return. Otherwise you have found a cycle, then what you do is you simply start from the end when the end is not equal to start. Since you also have to print the size of the cycle, so you store it in a vector, let's call it cycle. So in the cycle you push the end node. Now while the end is not equal to start, you keep moving to the previous node and you keep pushing the node into the cycle, right? Let's push end here, then end would be previous of end, and then I think we have to once you have this thing, yeah, now you push the start again, you know, you push this end, and then you, or what you can do it like this. First push the cycle, push back end, and then change the end, push it, keep on doing until the end is not equal to start, and yeah, finally you again push the end. Okay, and now you print the cycle dot size, and you print this is the size and followed by the nodes, right? Followed by the nodes. I hope I've done it right. Just push end, and then end is not equal to start. They are different, and when end is not equal to start, end becomes equal to start. Okay. Now let's implement the DFS thing. It's a boolean function, bool DFS and node. What else do we have here? -1 previous. So we have parent, and then we have this previous array. Then I have previous, after previous array what do we have? I think we have what I'm passing, visited graph start and end. Yeah, vector visited graph now here you're gonna mark the visited as true. Then for previous of node you will store this parent. If this is visited, so here you also have to keep track if this neighbor is not, if neighbor is same as the parent, then you continue. Otherwise you check if this neighbor is already visited. If it is already visited, you found the start as the neighbor and as the node, and you return true right here. You found a cycle. Otherwise you call this DFS again for this neighbor while the parent becomes this node. Previous is same, then pass visited, then pass the graph, then pass as a graph we have vector of vector. Okay. And then you pass the start, and then you pass the, so if this returns true you return true, otherwise you return false. I hope it is clear. Maybe in the next video we'll use some visualization tools to understand these algorithms better, and but we'll see that in the next video. Let's try running this code. Nothing's wrong. I'll push end here, then let's store the end in some current, and then let's push the end. Five three one one. Not end, current you need to push. 531. It should be 5315. Yes, 5315. Yeah. Let's try submit. Yeah, so I was making a mistake. The mistake was this. So once I push the end here, I'll have to push the same end here. Like I'll have to push the last node as the starting node, because that's when the cycle completes. So I have pushed the end here, then at the end I have to push the end here as well. So I have to temporarily store end somewhere. Okay. Rest everything is okay and working fine, and yeah. So it's again like counting the connected components, you're visiting every single node exactly once. So time complexity will be big O of n plus m. Same goes for the space complexity, like big O of n plus m, right? And I hope that clears the any doubts for this problem round trip. And next problem is, I think, labyrinth. Again we visit the labyrinth. Reach one boundary score. We'll solve it in the next video. We'll solve this problem in the next video, that is monsters. I hope you learned something from this, and now you are, you have a better understanding of depth first search, and you know how to detect a cycle in a undirected graph. Keep it in mind. Make a note of it in your mind or somewhere else, or some like use somewhere you put it somewhere in notes or in your mind or in Notion or whatever, that whenever you want to detect a cycle in a undirected graph, you got to use DFS here, plain normal DFS, similar to finding connected components. Okay, so that's all for this video. I'll see you in the next one. Till then, take care. Bye bye, ladies and gentlemen.